Très bien. Moi, je vous propose qu'on commence. Donc, je suis très heureux d'introduire Olivier Rioul, qui est professeur à Télécom Paris, qui est un spécialiste de théorie de l'information. Et donc, nous avons profité du fait qu'il avait à la fois une invitation du Lynx et une invitation du PC Founds du PEPR pour avoir ce premier séminaire commun Founds Lynx. Et donc, c'est une première, Olivier. C'est quelque chose de, je pense, très utile à notre communauté à nos deux communautés. De Lynx, comme vous le savez, est dans les locaux de Télécom Paris et Rioul est évidemment à un étage de différence avec le Lynx. Donc, il y a tout un ensemble de nouvelles connexions à établir. Et idem pour la partie Founds, dans laquelle la théorie de l'information est une composante absolument essentielle. Donc, je suis très, très heureux de cette première. Je remercie Olivier d'avoir accepté la double invitation et et de lui donner ce format. Alors, aujourd'hui, Olivier va nous parler de Alpha Information Theory. Donc, je lui donne la parole et je remercie Haroun Padakandla de Eurecom, qui a été le grand facilitateur de cette première. Merci, Haroun.
Merci beaucoup, François, et merci Haroun pour
Merci,
ces
merci.
invitations croisées. Je ne sais pas si je dois continuer en français parce que maybe I should switch to English, huh? Shouldn't I? Okay. So let's start it all over again, maybe? No. Okay, so I will be talking about alpha information theory. So you'll know what this alpha means. And I will be applying these information theoretic results to cryptography, and particularly side channel analysis. So how can alpha information theory formally prove that your sensitive circuits, integrated circuits, for example, are protected against side channel attacks? So let me see whether I can. Okay, so this is a joint work with my PhD student, Julien Beguineau, who's finishing his PhD this year. And so as a general introduction to the subject, so as you know, cryptography is no longer just a military science. Okay, it's everywhere, every day in our digital society. It's not thinkable not to authenticate yourself or give a service or protect your data in some cloud medium or whatever. And in particular, we know from the 19th century the basic principles of cryptography, right? So we know in particular Kerckhoffs' principle, also referred to as a Shannon maxim, which says that we have to assume that the adversary knows the system, the crypto system entirely, and so that the security of the system must be based exclusively on the secret key. Okay, and so today's cryptographic algorithms based on number theory, elliptic curves, whatever, lattices, and so on. We can assume that the mathematicians have done a great job. Okay, so that essentially the secret key cannot be recovered from plain or ciphertext, and even with quantum computing. So that essentially to actually break a system would require a brute force try of every possibility of the key, which takes several times the age of the universe, and so we're good. However, you may have seen these several examples of attacks, and actually every day has its own attacks. Like, for example, the American embassy in Paris, which was spying on the Élysée from the roofs of its embassy. I don't know if you heard of that. That was several years ago. Another example is the meltdown or spectrum, like a major flow in the Intel processors several years ago. And it was really infamous in the industry because they the companies had to implement hardware patches for all generations of processors. And even last year, there was another flaw called indirector, which is a major concern. And also, as another example, you have this, I don't know if you know this key tapping algorithms that is simply listening to the sound of the clicks that you make on your keyboard, on your computer keyboard, and he's guessing what you're typing from that. Okay, so all these has something in common, and they're physical attacks. The physical attacks, they're called side channel analysis. So it's not a mathematical attack, it's a physical attack, which means that you exploit the physical leakage that is coming out of the implementation of algorithm. You don't want to try to break the algorithm, you just want to try to exploit the amount of information leakage that you get from the implementation, hardware or software. The first example of this was by Kerckhoffs back in the 1990s. And it was simply a timing attack. You simply, so it turns out that for RSA at the time, the crypto algorithm takes just a little less time when the secret key bit is 0 than when it is 1. And so you just have to time the execution time of the algorithm and to guess the key bit by bit like that. Very simple. You don't actually attack the RSA. You just listen to what's going on. And another type of a side channel leakage is like, for example, power consumption or any type of electromagnetic leakage that you can have, emanation of the circuit. Like you give me your phone and I probe it while it's executing the crypto algorithm using a probe or antenna. I get some noisy signal, which is correlated to somehow to the secret. And using models, using some statistical analysis, I can guess the key in a divide and conquer approach, like bit by bit or byte by byte, something like that. So this is a major threat today, side channel analysis. And yeah, this is how it's going on in practice. Like you have a circuit and you probe it and you get a noisy signal like this. So it could be like additive noise, Gaussian noise, or it could be another type of model like erasure noise. And at any rate, you have some models and you can use them to actually break the crypto system like this. Okay. Okay. So, of course, you have countermeasures as well. It's been 20 years that people have been working on this, so you have some countermeasures. And one of the main countermeasures for, to prevent such attack is to do some secret sharing, if you like. Like you have the 1 byte of the key that you split into several shares, which are taken randomly, uniformly, and then you do the computation for each of these shares, and at the very end you combine those shares to get the secret key again, or to get the secret information again. So this is how it works. It doesn't mean that it's not prone to attacks, because you can actually every share is leaking somehow. So you can do like a multi-dimensional attack by putting several probes, several parts of the secret, and carry out a multi-dimensional attack, which takes more time, but it's still feasible. Okay. So this is how it's going on. So the big principle that the takeaway message would be, it's not a question of whether you're secure or insecure. You're always insecure at some point. It's a question of, it's just a matter of time. So the question is not whether you're secure or not. It's the question of what is the actual level of security that you can handle with your implementation. Okay, and so that's why we need some formal derivation, formal proofs that you have this or that level of security for a given implementation. Okay. Okay. So yeah, so the thing is, before we were doing that research, the chip designers would tell us, okay, I've got a chip and it's very secure because I've implemented a second order masking, for example, and I tried this or that attack and it didn't work. So it's safe. But you cannot trust this because maybe you didn't attack the right part of the circuit, or maybe you weren't good at that. And so we need some form of proof that we can rely on. Okay. So that's the whole point of the research that I will be that I was undertaking using information theory to actually determine the level of security of any cryptographic circuit, given any type of attack, any type of attacker. Okay. So as I told you, this is not mathematical attacks, this is physical attacks, but we can do a mathematical analysis of such a physical attacks using essentially communication theory, like for Shannon, you know. So and I was quite amazed to see this striking resemblance between communication channel, the classical communication channel, and a side channel. You know, side channel, it's not a communication because you don't want to communicate the secret, right? But it's like you have a source message which is not it's not there to be communicated, but it's the secret key, and you have some encoder, which would be the way that the device is leaking, which somehow is not known completely, and the side channel, which is like, for example, measurement noise when you try to probe the signal, and the decoder would be the attack itself, which tries to decode, try to attack to recover the key. Okay. Okay, so will Shannon do something for us in this situation? That was the question. Okay. So as a formalization, we have more precisely this. So we assume that we have some random variable, which is
Yes.
Can you mute yourself, please? Okay. We have some random variable, which will assume random or uniformly taken at random because, well, the attacker doesn't know anything about the actual value of the secret, right? So this is key. We have some sensitive variable, which is used in the algorithm. So we know exactly how the algorithm works, right? And this is called a sensitive variable because it depends on the secret. And this is the side channel, so like a measurement channel, and Y would be the leakage that is measured and used by the attacker to guess the key. So this is the simplest model that we have. All right, this is like a Markov chain here, K, X, Y, K hat. But then, of course, we have to also take into account the actual plain or ciphertext that the device is using to carry out these cryptographic algorithms. So this is like a spy information, if you like. It's called T, which the attacker may know, or may even choose sometimes. And we have several uses of the channel. Okay, we can do many measurements during the execution of the algorithm. And this is the parameter M here. The number of measurements would be M. Okay, so these are vectors here of size M. And so we get a lot of M different values of the leakage used by the attacker to guess the key. So the Markov chain takes this form in this notation. Okay. And so what would be the best possible attack? So we know the best possible attack would be to carry out a maximum a posteriori probability rule, MAP rule, which simply guess the key as maximizing the a posteriori probability, the K given the observation, which is Y, and the knowledge of the text, T. Okay? So as a countermeasure, we have this secret sharing scheme, which is called masking, where we want to split all the variables into different shares. Like, for example, X would be split into D+1 share. This is D-order masking. Okay. And so X would be the sum. So in some additive group, so it would be like, for example, XOR, you know, bit-by-bit XOR addition of different shares, x0, x1, and until xd, where all these variables are uniformly random, okay? But they have to sum up to x. Like, for example, you take d uniformly distributed bytes, and you compute the sum or the difference between x and the sum of the d, and you get the last d+1 share. Okay? So d equals 0 means unprotected device. There's no masking. D equals 1 is the usual first order masking. And then you may have like second order and so on. Okay? So the thing is that every share is statistically independent of the sensitive variable. So using only just like at most d shares, you cannot recover the secret. You have to have some leakage about a d+1 share because they all combine to give you back the secret. All right. So now each share leaks. Obviously, everything leaks, all right, in implementation. So you always have, I don't know, some electromagnetic emanations or whatever. And so you have d+1 side channels instead of just one. And so this is the kind of channel that you get, memoryless type of a channel. Okay. Now from this, so the Markov chain now is more complicated because this x is a sensitive variable, and the boldface x here represents every instance of d+1 shares. Okay. And so it's a dimension d+1 times m, if you like. But all these are independent and identically distributed every time because the channel use of are memoryless. Okay. Additive, white, Gaussian noise, whatever. Okay. So this is the basic setting. And so what is the purpose of masking in this case, where it's simply to ensure that the attacker would need a prohibitively large number of measurements to actually break the system. And we hope to achieve that for any type of attack. Okay, could be, so the best possible attack in theory would be the map, but the map rule cannot be carried out in practice because it would require to know what is the actual adversarial probability, which is a very difficult task because you don't know exactly how the device leaks and so on. But at any rate, if you are secure against map rule, then you're secure against any type of attack. Okay. So for that, we need to have several choices. So the first choice is how you can measure that the attack is good or bad. Okay. So in the side channel literature, you basically have two criteria. And the most common, the simplest criterion is simply the probability of success. 1 minus the probability of error, if you like. If you're using communication, probability of error is a well-known criterion. Here they use probability of success given by the map rule. The other criterion would be the guessing entropy, which is also interesting as in its own right. It's the average number of tries that you have to make before finding the actual value of the key. But we will be using essentially this success probability in this presentation. The guessing entropy is more difficult to actually handle. Second, we need to choose the type of information measure, okay, information theoretic measure, to actually measure the amount of leakage. Okay, so we have many choices for that. The obvious choice would be mutual information, but we have many others. Okay. So I called it L as information leakage between K and everything that the attacker would know, which is the leakage, the information, the leakage that he measures, and the text that he knows. Okay, so these are just examples of information measures that people have used in the literature. Mutual information is one such information measure, of course. People in cryptography have used a lot total variation So it corresponds to total variation information, as we call it, TVI, between two random variables here, which is defined essentially the L1 norm between the joint distribution and the product of marginals. Maximal leakage was used recently also, and we'll see the connection with the others. Some people have used a Euclidean norm or relative error, average relative error, but many definitions have been proposed in the literature. And we have proposed this as another criterion, which was found to be optimal in some respect. So I will not go through the details of this, but it's also interesting. It's called the Dublin coefficient. It was proposed last year in the crypto conference by Julien, my PhD student. Okay, so here in this talk, I would like to talk about alpha information, which is called Simpson's alpha information, to be more precise, because there are several types of alpha information. And alpha is a parameter, is a real parameter, which is generally not zero, but it could be negative. Often it is positive, and alpha equals 1 reduced to the known case of Shannon's mutual information. Okay, and alpha can tend to infinity as well, or to minus infinity. Okay. So what do we need as a general methodology? What the general method to actually achieve our goal, which is find a lower bound on the total number of measurements that the attacker needs before breaking the system with some probability of success, is to do the following. So we have several ingredients. Every ingredient yields an inequality. The first inequality is called, it's what I call Fano inequality. So maybe you don't recognize Fano inequality here, but Fano inequality in the classical case is simply a lower bound on mutual information, where D here would be the Kullback-Leibler divergence, the binary Kullback-Leibler divergence. But it could be any distance or divergence between the probability of success given by the map rule and the probability of success 1 over m that we would have without knowing any information, okay? Because you have m different choices for the key. Okay, so this is the first ingredient. Second ingredient would be this. So here we exploit the fact that we know the text, and the text can be put on the left of the semicolon here instead of on the right. This is a quite technical lemma. The third ingredient would be data processing inequality. So data processing inequality says, okay, you have a Markov chain, and as a result, the leakage observation depends on the key on the text only through the sensitive variable, because that's the input to the side channel. Okay. Next ingredient is tensorization, what I call tensorization. It means that if you're using the channel n times, then the leakage measure between vectors of size m would be simply m times single letter expression of this leakage. Okay, this is only for some types of information leakage, we will see. And the most important step now is Mrs. Gaber's lemma. So I don't know if you know about this, Mrs. Gaber's lemma. It has an interesting history. It was used for the first time by Weiner and Ziv back in 1973 to actually find capacity regions of some broadcast channels. They use it Mrs. Gaber's. You know why? Because actually Ziv was visiting Weiner or the other way around at Bell Labs. We were talking about Bell Labs. He was coming from Israel to Murray Hill, Bell Labs, and he stayed in a house, in Mrs. Gaber's house, and Mrs. Gaber's would always come and talk to them and so on. And so they were working on this particular lemma in a very special case for entropy, for discrete entropies. And that's why they used the name Mrs. Gaber's lemma as a private joke. Anyway, so Mrs. Gaber's lemma is very important here because it says that you can bound the information leakage of the whole story here by the product or something similar of information leakage for each share. Okay, and that's important because in general you cannot evaluate the whole leakage because it's you have this dimensionality curse here, it's too high. But you can actually try to evaluate the information leakage share by share. It's much more easier. Okay, so there's inequality going in the right direction here. And finally, combining all these inequalities, you get this thing, okay? You combine everything, and you get this divergence between PS and 1 over m, or this type of distance here, in the numerator. And in the denominator, you get the product of leakage share by share. And that's the lower bound on the total number of measurements that the attacker has to make. So that's the general methodology that we'll be using. So I will now detail every step for alpha information. So first I need to define it. Okay. So this is just before that, this is the practical result that we shall send to the chip designer. Okay. So what it says, okay, here we have the probability of success and the number of measurements. So eventually, when the number of measurements tends to infinity, of course, you get a probability of success 1 that you get the secret. We're never secure. Okay. And the Ziegler curves here are the actual attacks that can be mounted on, ML attacks that can be mounted on some specific devices. And what we can compute from this equation here, from this inequality, are this dash dotted lines. These are upper bounds on the probability of success for a given number of measurements, if you like. So we know that any practical attack cannot go above this. Okay, so like we have a formal proof for any type of attack that it cannot do better than this. Okay, and the different colors correspond to different orders of masking. So that would be no masking at all, so unprotected implementation. That would be, let's say, D equals 1, D equals 2, and so on. Okay, so that's why that's what we're selling. Okay, now how we can do that? We have to carry out some basic properties, information theoretic properties of alpha information. And to do that, we need to, first review some definitions. So maybe these definitions are not well known, but for alpha equals 1, they boil down to the classical Kullback-Leibel divergence and so on. So we consider this type of kind of scalar product, if you like. And this absolute value of alpha accounts for the fact that alpha may be negative. Okay, and so we have this definition for the alpha divergence between two probability distributions, P and Q. All right, if you let alpha tend to 1, you get the usual stuff. Okay, now we obviously have some reflection formula. If you exchange the roles of P and Q and alpha and 1 minus alpha, and from that you can have some reflection relation between D alpha and D 1 minus alpha, and you can easily prove that it's always non-negative quantity.
The manufacturer, then it says, for example, it's like 6 pounds after my.
Okay, thank you. Side channel attack. So we know that alpha divergence is always non-negative and can only be 0 when the two probability distributions coincide, which is the usual property that we have, right? Okay, now we can define alpha information. To do that, we consider the alpha divergence between the unconditional distribution Px and the conditional distribution of x knowing y. Okay, and we want to average this over taking the expectation over y. Okay, but we don't do that directly on this. We do that inside the log for some reason. And the essential reason is that the resulting alpha information has all the nice properties that we want. Okay, and so this gives the definition of Simpson's alpha information. In fact, Simpson himself, back in 1969, defined alpha information in a much different way, but it amounts to this formula. Okay, so he actually defined this as minimum of alpha divergence between the joint distribution and the product px times qy minimized over qy, which is rather more difficult to understand. Anyway, so alpha equals 1 gives you the enriched information, of course. Alpha equal plus infinity gives you the Island-Wagner maximal leakage, which was used also for side channel analysis, information leakage. Alpha equals minus infinity gives you the complementary doubling coefficients that were recently proposed. And so, yeah, it's all these nice properties that we have. Okay, so of course it's related to alpha entropy, which is the Rényi entropy. Rényi entropy is defined with this formula. So again, we take into account the fact that alpha may be negative here. Okay, and alpha is the norm. The alpha norm is given by this formula. So it could be integral or it could be sum. I have to say that because mu is like the dominating measure. So it could be Lebesgue measure, and then you have integrals for PDFs, or it could be like countermeasure, and then you have sums, discrete sums for PMF. Okay, the corresponding conditional entropy, again, we have to take the conditional distribution and average inside the log, and that's called Arimoto's conditional entropy, which is well known in some cycles anyway. You may have some other definitions of conditional entropy as well, but we can establish that for uniformly distributed X, or like uniformly distributed T, for example, the alpha information is simply the difference, the usual expression between alpha information and alpha entropy, sorry, and alpha conditional entropy. But this does not work for non-uniform X, but yeah. Okay, so what is Fanon inequality? The classical Fanon inequality, 1952, is this thing. So it's an upper bound on the conditional entropy for a given probability of error. I guess you're all familiar with this, so more or less. It's been used several times for proving converse theorem, converse coding theorems. And this is equivalent, exactly equivalent to finding a lower bound for uniform X, a lower bound on mutual information as the Kullback-Leibler divergence between the probability of success and the probability of success without knowing anything, which is just 1 over n. So this is an illustration of this. So this is the Kullback-Leibler divergence here, okay? And so the mutual information is always greater than the divergence between the probability of success and 1 over m here. Okay. Okay. Of course, we can generalize this to alpha information, essentially with the same simplified proofs using data processing inequality for divergence. We'll not go into the details, but you can see quite easily, and this has been published some years ago already, that the alpha information is never less than the alpha divergence, which I defined previously, between the actual probability of success using the map rule and the one not knowing anything. So these are illustrations of this for different values of alpha, okay? And in particular, you have this for alpha equals infinity or alpha equals minus infinity, and these are interesting inequalities that you can have. Right? All right, now the text switching inequality is more technical. So if you're not familiar with all this stuff, I will probably not go into the details, but essentially you can use the Simpson definition to actually carry out a simple proof of this. So the fact that T can be taken from the right of the semicolon to the left. Okay, this was needed. And the more interesting inequality is the data processing inequality. So simply we have a market chain like sensitive variable, leakage, and let's say any market chain X, Y, Z, T. Okay, you know that the alpha information, the information between two random variables which are further apart in the Markov chain is always less, can never be actually greater than the mutual information between random variables which are at a smaller distance, let's say, in the Markov chain. Okay. And if we apply this to our Markov chain, we obtain this, okay, meaning that the alpha information of the leakage with respect to the key and the text is less than the alpha information between the leakage and the sensitive variable. That leakage comes out of the sensitive variable using some noise. Okay, tensorization is also very easy to establish because of these memoryless properties of the channel. And that's why we have this M here. We have a factor M that comes out because the channel is used, let's say, independently every time. Now, Mrs. Gaber's lemma, that's the most interesting part. So Mrs. Gaber's lemma, Mrs. Gaber's lemma is easy to establish for the binary group when you have simply bits, okay? Suppose that you have any Bernoulli random variable, two Bernoulli random variables which are independent, and you sum them. So you sum them into the group, that is, you sum them modulo 2, okay? And then the Bernoulli parameter of the sum is simply the binary convolution of the two Bernoulli parameters of each one. And therefore, you have an equality, in fact, given by this expression here, where H is simply the binary entropy. Little h, lowercase h is the binary entropy. The classical Mrs. Gaber's lemma in this context is this inequality here for conditional entropies. And this is due to the fact that it can be shown that this expression here is convex in one variable when the other is fixed. It's not necessarily jointly convex, but it's convex when one of the variable is fixed. If you use it twice, you get this inequality here because conditional entropy is simply an average value of entropies. And that we'll need for the following. So we can reformulate this well, if you have several shares, first of all, okay, if you have d plus 1 shares, then you get a product like this. And it can be, again, rewritten as this inequality as an upper bound on the mutual information as a kind of product. So it's not exactly a product, except when the information is small, because phi of x, or because of this nonlinear function here. Okay, so this is exactly equivalent to Mrs. Gaber's lemma. Okay, and to establish this, we actually diagonalize the binary convolution using a DFT of length 2, and so the binary convolution becomes a product. Essentially, that's the trick. Okay, well, now we can generalize this to alpha information. Okay, this is, of course, much more complicated. I will not go into the details here, but essentially there's no, let's say, theoretical difficulty here. So we have inequalities on one side, also on the other side, depending on the values of alpha and on the properties of this special function here. So we are able to establish all this. So depending on the value of alpha, if alpha is increasing or decreasing, and so on, we have these inequalities here. Okay. We published that recently as a book chapter. Okay. So, yeah, putting all this together, okay, we get Fano inequality, text switching inequality, data processing inequality, tensorization, and this is Gaber's lemma, and we end up with this inequality here. Okay, so we are able to have this inequality provided that alpha is not between 1.5 and 1 and 1. Oh, sorry, 0.5 and 1. Okay. Right. So yeah, so that was for the binary case, and we have to extend this to, you know, any value, let's say m equals 2 to the n, and it turns out that we have all these inequalities here that I think similar inequalities we can prove using extension of Mrs. Gaber's lemma, not for the binary group, but for groups of size cardinality 2 to the n and so on. Okay. Okay, so these are the actual results that we have. So if you like, for example, if you take bytes, key bytes, so m is 2 to the 8, and you have some side channel which is given by, okay, so this is a classical leakage model that is being used in the side channel literature, which is that it leaks, so you have a deterministic part which leaks like the Hamming weight of the sensitive variable, of the byte of the sensitive variable, plus some Gaussian noise of variance sigma squared. This is called Hamming weight model. So for this classical case, you end up with these curves here. So what is given here is the advantage that you have PS1 minus 1 over S, the advantage in terms of success probability with respect to the case where you don't know anything, to the blind case, if you like, as a function of the number of measurements in a logarithmic scale here. And you can use it for all these information measures here. So many of them are alpha informations, but you may also apply this to other types of information measures like total variation and so on and so on. And so you can choose the actual type of information leakage that is best for your application, if you like. That gives you the best bound here, okay? So similarly, this is what happens when the noise increases. So sigma equals 5, okay? Standard deviation of the noise. And sigma equals 50, where you have essentially what is best in our approach is either, well, depending on the number of measurements. So it's either what is called mutual information of order 2, okay? Or it can be, you have to, yeah, it's not clear whether it's, sometimes it's I, sometimes I minus infinity. But anyway, you can play around with all these notion of information measures and actually find out which is the best that you need to obtain your result. Okay, so all this has been actually published in a chapter in the honor of Andrew Barron. And so you have all these technical details on alpha information theory and application to side channel analysis there. So I hope I was not too technical for you, but essentially the basic ideas are there. So what is important to understand is to actually have the have the correct notion of information measure that gives you all these interesting inequalities that you exactly need to have a lower bound of number of measurements that the attacker needs to break the system. Okay, and this is the nice part of the research. Okay, and it holds for any type of attack, which is really fine. But before that, people have tried to, you know, do countermeasures for a given type of attack, and so every type of attacks you need to redo all the work. And here, due to information theory and essentially due to the converse part, converse coding theorem, if you like, part, like Fanon inequality and stuff, you get a result which is completely generic, that is valid for any type of attack. Okay, so many of our mathematical elucubrations are within this book, which was recently published in Springer, Mathematical Foundation of Side Channel Analysis of Cryptographic Systems. If you want to have a look at it, I have some copies in my office if you want to pass by. Okay, and merci beaucoup. That took me 45 minutes.
Thank you very much.
Okay.
Okay. So questions, please.
I'm not from this domain, so it's just out of curiosity, two questions. So one is, so you found these generic bounds, but you said that before people were trying to characterize a specific type of attacks. So did others managed to find some bounds, but in particular case, and you found that your bound is more general, but it doesn't contradict what others have been done.
Now, what they did was like, okay, I have some leakage model, and I carry out a certain type of attacks, like, for example, it could be correlation power analysis, as they call it, or it could be mutual information analysis. So they carry out this type of attacks, and they obtain some result. Okay? They obtain a minimum number of measurements that you need to achieve a certain probability of success. Okay, and that's about it. That is so with some countermeasure, without some countermeasure, you get this result specific for this type of attack and specific for this type of device.
Okay, so it was fully experimental, empirical.
Yeah, almost, yeah. So yeah, it could be also done with simulations.
Yeah.
And some real data as well. Yeah.
So maybe the second question, maybe you answered already. The slide that you showed as a selling points. So I understand what is the first one that you showed, the green and the red.
Yeah, sure.
Yeah, this one. So I understand the dotted curve. It's your bound.
Yeah.
But the other curves, are they obtained by simulation?
So these are from specific device which actually know the leakage model. So this comes from simulations, in fact.
Simulations.
And we carried out a map attack, like ML attack, in fact, because the different values of the keys were uniformly distributed. So the map corresponds to the ML, maximum likelihood.
Okay.
Yeah. Sorry.
Yeah, still on this figure that I like very, very much. So I'm not in the domain also, but I can understand at high level. We see that the theoretical limits are very close to the experimental ones or by simulation ones. Do you have some means to estimate or the difference between what you expect to find by simulation and these bounds? Because these bounds are only bounds. You don't know.
Sure.
Maybe you don't know
Sure.
how far you
That's
are
not
in
clear.
reality.
Yeah, that's not clear because it's based on a whole bunch of inequalities. And
Yeah.
so we don't know. We
It's
don't
quite
actually
good,
know what
even
we're
if it-
losing there. But yeah, but
It's
still
quite
the
good, in
result's
fact.
quite nice. Okay, so you
So-
can also say final inequality is optimal in some sense because
okay.
you can do
I see.
inequality and same for the other inequalities, but it's not clear for a given practical problem whether these inequalities are good. Yeah, it depends.
Hi. If you go to the other figure, the one with
The one in the end?
yeah, the very last one.
Yeah.
Yes, this one. So if I understand correctly, your leakage model assumes that the measurements are independent from each other and that they do not alter the system that they are trying to break. In the sense
do you
that,
mean?
I mean that the information that you obtain is already available. And for instance, you were making the example of the noise that you can get from chips and from devices, and it's not something that you can actively probe to obtain.
Yeah, no. This is just a model of what you can actually probe. So people were quite confident that this Hamming weight model was a very good first order approximation of the type of leakage that can type of leakage that you can have in practice, because in fact what is happening inside the algorithm is that the sensitive variables are put in some registers, and these registers are leaking somehow with some electromagnetic emanations every time corresponding to the different bits in the register. And so the total leakage is essentially the Hamming weight, so sum of the bits.
Mm-hmm.
But that was just a model for simulations, but still, it's apparently a very good approximation of what is actually going on. And the Gaussian noise is also very standard type of measurement noise that you can have. So it's not bad. It's not so bad.
So thank you.
Laura.
Hello, can you hear me?
Yes, I can hear you.
Yes, I have a question. So you said at some point that if you are secure against map decoding, you are secure against all other attacks. So I think here you're assuming that the goal of the attacker is to guess the whole key. But what if they only want to guess a certain number of bits, and then with these bits they want to launch a cryptographic attack, for example?
Sure, sure. So, okay, so you have actually two questions in one. Like, okay, so I was assuming that we want to target a specific key byte, a key chunk. Okay, as if we have all the bytes, then of course we can have the whole key. All right, but essentially what is happening using your embedded crypto system is that they work byte by byte because okay, it's a lightweight cryptography. And what you say is also related to the notion of guessing entropy. Okay, so which is another criterion which I did not talk about in this presentation. So we were only interested in, okay, maximizing the attacker wants simply to maximize the success that he guesses a given key byte. That's it.
Okay, it's for a key, it's for a chunk of key then.
Yeah, for a key chunk, yeah.
Okay, I see.
Oh, go ahead.
Okay, so again, on the first plot that you have,
Yeah,
it's
sure.
a curiosity, but it seems that you have your bounds that are tighter than for D equal 2. The orange.
For D equals 2, yeah.
Yeah. So is this a sign of something or?
Yeah, that was a very specific example, so it's not to be taken too seriously. Okay, but yeah, so.
But yeah, I maybe I'm
And these
completely.
bounds have been improved over time as well, because we were okay. At first we worked with misinformation, and we worked with some other information and so on, and then we were able to do like generic bounds. So this was I think this is taken from an article 2 years ago where we had some loose inequality because of the use of Pinsker and reverse Pinsker inequality. So it's not exactly fit. So it has not to be taken too seriously. Just the concept is there. Yeah.
I had a question, but perhaps other questions online?
No.
No? Okay. Yes. So I mean, there is this alpha parameter.
Sure.
And when you look at all this alpha information, I mean, can one get a sort of physical sense of what the alpha parameter means in practice, or intuitive way of tuning alpha?
That's a good question. So we have some interesting properties for different values, specific values of alpha. So alpha equals 1, you know about.
Yeah.
Alpha equals 2 generally corresponds to the notion of collision attacks in cryptography. So there is some link with that. Alpha equals infinity corresponds to what Issan Wagner proposed. So it's related to also kind of maximum likelihood attack. Alpha equals minus infinity. We are able to find out the theoretical properties that is optimal in some sense using erasure channel. So a doubling coefficient, maybe you know about this. The doubling coefficient allows you to prove that the best erasure channel model is the one given with parameter given by this complementary doubling coefficient. So for every alpha, you have some nice property. But
the global picture.
The global picture, we have no specific. I mean, no specific idea, except that it was nice that it fits the common derivation. But we have all these nice properties. This is Gaber's lemma, data processing, Fano, and so on. But it's not stable yet. We also have some link with guessing entropy. So guessing entropy is related to alpha information when alpha equals 1/2 asymptotically. So yeah, we have some partial results like that. But what do you mean a global picture? You know, it's difficult to say.
The single parameter varying from -infinity to infinity, and so.
So yeah, so what we can say is that the alpha information increases when alpha increases. something like that. Yeah, we don't have that many that much understanding of this. Yeah, except for very specific cases.
Very beautiful and very mysterious.
Yes, well, that's why it's interesting, right? It's mysterious. But it also has a connection with people working in communication theory because it has some connection with the Gallagher exponent as well. So yeah.
Any other question online?
I had one question. Just also adding to Professor Francois' question. I think the alpha information also, as Professor Rioul mentioned, it is very much linked to the error exponents in either the Stain's lemma or the error exponents in the channel coding. And really, I mean, it's very interesting to see that the alpha equal to 1, the standard Shannon information is really just an average case analysis. But if I take alpha to infinity, let's say, in the Rainy information sense, it gives you a sense of like the kind of the divergence between the max probability and the average probability kind
Exactly.
of.
Yeah.
And my question is like, how is this Simpson information related to the Rainy information for which, well, Rainy doesn't have an information measure. He only talks about an entropy measure, but how is it related? Because the Rainy entropy has a little bit more kind of, nice sense from the Stain's lemma and the Gallagher exponent.
Well, it is related. You have the way we relate it in this work was to assume that the sensitivity variable was uniformly distributed. And in this case, we have a very simple formula between alpha information and a conditional alpha entropy in the Arimoto sense. So the sense that Arimoto used it for a coding exponent. So yeah. But apart from that, I mean, all this is complicated. Okay, so in general, you don't have a very simple relationship between alpha entropy and alpha information, like we have for the case alpha equals 1.
One quick question. So, what was the motivation for Simpson's this definition? What was his kind of viewpoint when he defined this?
Ooh, I don't quite remember, but he done a paper in 1969 called Information Radius, and I don't remember quite well what was his motivation. But it turns out that this was a natural definition in this context, and it turns out that it has all these interesting properties that the other definition of alpha information that exists in the literature don't have. So it turns out to be the best definition for me because I needed all this.
No, thank you. That was good. Merci beaucoup.
Merci.
Okay, so any other thoughts or comments or questions online here? Okay, so let's thank Olivier.
Thank you.
Beautiful lecture.
Good. Thank you so much for attending.
Professor Francois, thanks a lot for all the arrangement. Thanks a lot for the talk. It is from PEPR. I would really thank you. There were a lot of audience, so thanks a lot.
You have to iterate that again. Thanks to you.